In this video, we're going to find the mass of a thin wire that's lying in the xy plane, and its profile will be given by the curve y equal to the square root of 9 minus x squared along the interval where x is varying from 0 to 3. As we move along the wire, the density is varying according to this function that I'm going to call delta. And delta is telling me the density, it's x times the square root of y, and that would be in units of something like grams per unit of length, mass per units of length. So I'm just going to say grams per centimeter. So first, let's draw a picture. It's sitting in the xy plane. I'm going to think about what happens when x is 0. And when x is 0, my y value will be square root of 9. It will be 3. So I'm going to plot this point right here. And then when x is equal to 3, this y value here will be 0. And so I'm going to be at the point 3, 0 on the x-axis. My arc is in fact a part of a circle, and it's going to really, we're seeing like a quarter of a circle here. Maybe I haven't drawn it so well, but it should be connecting these 2 points together. And again, the defining equation is y equal to the square root of 9 minus x squared. So the very first thing that we're going to need to do is parameterize this arc if we're going to do any meaningful calculations. There is no single way to do this, but there is kind of an obvious way to do it. My curve is given, y is given as a function of x. So as I vary the x-axis, my y-coordinate responds according to this equation. And therefore, one parameterization will be to take my parameter t to be the x-coordinate. So I'm going to take r of t, its x component will be t itself. And then to ensure that I actually stay along this curve, I just need to make sure that my y-coordinate is the corresponding value on this curve for that value of t. So I'm going to take it to be the square root of 9 minus t squared. Let's just confirm that this is doing roughly what we wanted to do. When I start with t equal to 0 here, I will be at the point 0, and then square root of 9 minus 0 will give me 3, and I will be starting at this point at the top of this circular piece. As I take t to be equal to 3, I'll be wandering down this curve, and then I'll eventually get at t equal to 3 to this point here, where I'll have 3 and then 0 here for the y-coordinate. And so indeed this parameterization is tracing out my arc, and it's in fact oriented along this path indicated by the arrows. Let's find the velocity of this path. That means to differentiate it. That will be a vector quantity, so I'll differentiate each component. Derivative of that t will be 1. And then I have 9 minus t squared to the 1/2. That will take a power rule with a chain rule as well. Simplifying that, it will be minus t over the square root of 9 minus t squared. Notice that the 2's canceled out. In order to apply the change of variables theorem for doing integration later on, for doing the line integral, we'll need to know the speed of the parameterization, which is the magnitude of the velocity. And that will be a scalar part that I get by squaring up and adding up the squares and taking the square root of the component. So 1 squared, and I'll square this. If I write 1 as 9 minus t squared over 9 minus t squared and find a common denominator here and actually add the expressions together, there'll be some simplification. I'll have 9 over 9 minus t squared. I'll let you do the algebra there to confirm, which is 3 over the square root of 9 minus t squared. We now need to know the density. We have a formula for the density in terms of x and y, but I need to know the density along the arc, meaning in terms of my parameter t. So the density is delta of xy. X along my arc is given by my parameter t, and y is given by square root of 9 minus t squared. So I'm going to evaluate my formula for the density, which is x, that's t, times the square root of y, which is the square root of 9 minus t squared. So notice there's 2 square roots here. One from the density function and one from my parameterization. So when I parameterize it, I get this awkward looking square root of square root. Don't fear that expression. They're both just powers. I'm taking 9 minus t squared to the 1/2 and then raising it to the 1/2 again. And if I take a power of a power, I multiply the exponent. So this is really 9 minus t squared to the 1/4 power, 1/4 there. So now we're going to integrate, do the line integral of my density function along this arc, and that will give us the mass. So we'll integrate along the wire. The function that we're integrating is the density, and we're integrating it along the arc. This is a line integral now. And take a moment here to appreciate the units. Delta is in grams per centimeter. That's a density. And then I'm multiplying this by ds in a sense. S is change in arc length. ds is change in arc length. That would be a length, and when I multiply the two together, I get a grams or a mass. I'm going to now apply change of variables, which will turn this line integral into an integral involving my parameter t. T goes from 0 to 3. I evaluate my density along the arc. That will be the formula we found above. And I multiply by the speed. This is change of variables now, and we integrate with respect to t. So what does that look like here? I integrate from 0 to 3. There is my density along the arc in terms of t. And here's my speed, so multiply by my speed and integrate that with respect to t. Fairly messy expression, but you notice this is to the 1/4 power, this is to the 1/2 power in the denominator. When I simplify the exponents, it will really be to the minus 1/4, so 3t, and then that 9 minus t squared to the minus 1/4. You can do this integral with a u substitution. If you take u to be 9 minus t squared, you have a factor of t there that you can use to carry out the substitution. If you do that, you'll get an antiderivative that looks like minus 2 over 9 minus t squared to the 3/4 power now. And I'll let you do the details there. That needs to be evaluated between 0 and 3. And again, I'll hide some details here. I used a calculator to get me a final estimate of this value, and it's about 10.39. And that is a mass, so that will be in units of grams.